What's up, everybody? Hope you're all doing well. Today we're going to be looking at 11 conservation of momentum review problems. I'll go ahead and put a link to the document below, and I would recommend trying all these problems first, and then if you need help, coming back and watching the ones you need to watch. Alright, let's go ahead and get started. So in this first problem, we have two cars coming together. They're going to collide. So one car is moving 8 meters per second. The other car is moving starting at rest. And then afterwards, they're going to kind of stick together. So you're going to have the 2K, 2500K sticking to the 1500K. And they're just going to move off together as one mass. So the first part is asking what's the initial momentum of the two cars. So we're just going to use our momentum equals mass times velocity. Now the 1500 is not moving, right? So its momentum is going to be 0. The other one, again, is just mass times velocity. So 2500 kilograms times 8 meters per second gets us an initial momentum of 20,000 kilogram meters per second. So that's the momentum of that car. It's also the momentum of the blue car, the combination, because the blue car is not moving. Second part is saying what's the momentum afterwards. Well, the momentum afterwards is the same as the momentum before, because remember, momentum is conserved here. So that means the momentum after is also 20,000 kilogram meters per second. Alright, knowing that, we can now find the final velocity of the two cars. So since we know that, again, the initial momentum is 20,000, the final momentum, well, the two cars are moving off together, right? So we could write this as, say, mass 1 plus mass 2 times the combined velocity afterwards. So the total masses, that's going to be, 2500 plus 1500. So that gets us 4,000. Okay, and so now we can find the combined velocity afterwards. 20,000 divided by 4,000 is going to be 5 meters per second. So the last question now is asking, well, how much energy is lost? Remember, this is what we would refer to as a completely inelastic collision. That means that the kinetic energy here is not conserved. So in other words, we're going to have some kinetic energy, we're going to end up with less kinetic energy, and whatever's left over, we're going to say, well, that's how much energy got lost. Okay, that's going to be like heat, sound, that kind of thing. So to find that, we just do our kinetic energy equation, right? 1/2 mv squared. And then we'll say that's equal to 1/2 mv squared, but this would be like the combined mass and the combined velocity afterwards. So before the collision, only one car has kinetic energy, that's the 2500. The other car has none, right, because it's not moving. So that's going to be 1/2 2500 times 8 squared. Then afterwards, remember, their masses are combined, so the total mass is 4,000, and then the velocity here was 5 that we just calculated. Okay, so let's go ahead and do this. So 1/2 2500 times 8 squared gets me 80,000 joules. So that's how much kinetic energy we start with. And then 1/2 times 4,000 times 5 squared gets me 50,000 joules. That's how much kinetic energy we end with. And as you can see, we end up with less kinetic energy. So that means we lost some. So if we subtract those two, that's going to give us our energy lost. So we can do this in our head, right? 80,000 minus 50,000 gives us 30,000 joules of energy lost. All right, let's move on to question number 2. So this problem is similar to the last one. We have two carts colliding. This time, though, they're on a head-on collision. One's moving to the right, one's moving to the left. They're going to stick together afterwards. So again, we're going to have this kind of combined velocity afterwards. Now the direction should be kind of obvious to you. This one is bigger and it's faster, so that means it has more momentum to start with, so the final momentum should also be to the right. So anyways, we'll just set up our P initial equals P final. The first one has a momentum of 10 kilograms times 6 meters per second. The second one is 2.5 kilograms. Now it is important to notice that it's moving to the left. So even though they don't tell you this, you should be noticing that we have a negative velocity here, and therefore negative momentum. So the first one would be 60 kilogram meters per second. The second one would be negative 3 times 2.5, so that's negative 7.5 kilogram meters per second. Now their momentum afterwards, the masses are going to be combined, right? So this is going to be 10 plus 2.5, or 12.5 kilograms. Oops, 12.5 kilograms. Okay, times their combined velocity. So the initial momentum, 60 minus 7.5, that's going to be positive 52.5. And then we'll go ahead and divide by 12.5. So that gets us a combined velocity of 4.2 meters per second. So once again, this is an inelastic collision, completely inelastic, and so that means there's going to be energy lost here, right? So actually, let me just shrink this down. So we're just going to look at the energy before, the energy after, and compare. So in other words, let's do it on the side here. So KE initial equals KE final. So the initial, now notice this time they both have kinetic energies, right? So individually they have kinetic energies, and then collectively they have one kinetic energy. So the first one we're going to go 1/2 times 10 times 6 squared. The second one we're going to go 1/2 times 2.5. Now remember, kinetic energy is a scalar value. That means there's no such thing as negative kinetic. So notice even if we plugged in a negative, since we're squaring it, it's going to end up being positive. That's going to equal 1/2 mass 12.5. and then that combined velocity of 4.2 squared. So let's go ahead and calculate the kinetic energies. So the first one, 1/2 10 times 6 squared, that gets me 180 joules, plus 1/2 2.5 times 3 squared is 11.25. So that's our starting energy, which is 191.25 joules. And then our entering energy is 1/2 times 12.5 times 4.2. That gets me 110.25 joules. Okay, plus whatever's left over, right? And that's really what we're solving for. How much energy is lost or changed to heat, sound, etc. Okay, so we'll just kind of subtract those two, and it looks like we're getting 81 joules. All right, on to the next one. So in this problem, we have our ice skater is going to throw a snowball. So she starts with a snowball. She's going to go ahead and throw it afterwards. Okay, and then we just want to find out, first of all, how fast is she moving afterwards. So again, we'll just use our conservation of momentum. P initial equals P final. Now the initial momentum, this time the masses, we're going to kind of combine the masses ahead of time, right? So for example, the total mass of the skater plus the snowball is 95.15. And then her velocity is 2.5 meters per second. And then afterwards, right, let's write it up here. Afterwards, we have the momentum of the skater plus the momentum of the snowball. So in other words, we have the mass of the skater, which is 95, times her velocity, plus, now the mass of the snowball is only 0.15, and the snowball is going to be moving 32 meters per second. Okay, so let's go ahead and do this out. So 95.15 times 2.5 means the momentum of kind of the combination is 237.875. And then the momentum of the snowball afterwards is going to be 0.15 times 32. It's only 4.8. Okay, so notice it's not going to slow down a lot because there's not a lot of extra momentum this way. So we'll go ahead and subtract that out. So 237.875 minus 4.8 gets us approximately I'm just going to round it, 233 equals 95 VS. So the velocity of the skater, it's going to be very much the same, but slightly slower, right? Slightly slower. We're getting 2.45 meters per second. All right. The next part is saying, well, let's say the snowball is caught by another skater at rest. So this is really a completely separate problem, right? So here's our snowball. It's moving along at, what was it, 32 meters per second. And then we have our second skater who's going to catch the ball. That skater has a mass of 60, and they're going to be at rest to start with. Okay, so we'll use conservation of momentum. This time we only have the momentum of the snowball. Then afterwards we have the momentum of the combination. Okay, so we actually know the momentum of the snowball. So if you allow me, we'll just plug that in here. That was 4.8. And then the combination, so the new skater is catching the ball. So they had a mass of 60. We're going to add the mass of the snowball. So 60.15 is their mass times their velocity. I guess we'll write this as combo since they're combined. Okay, so it doesn't look like they're going to be moving too fast. 4.8 divided by 60.15 gets us 0.0798. 0.0798. Okay, very minimal. That's because the snowball is so small, right? The mass is so small compared to the mass of the skater. All right, moving right along. All right, in this problem, we have a skateboard. It's moving along at 5 meters per second. And we have a cat that's going to fall down onto our skateboard. And we just want to see what's going to happen in this situation. So once again, we'll use conservation of momentum. This time the momentum is just the momentum of the skateboard. And then the momentum afterwards, well, the cat is going to essentially add some mass, right? So we have the momentum of the skateboard plus the momentum of the cat times the velocity of the two things moving off together. Okay, so the momentum of the skateboard is going to be 1.2 times 5. Okay, that's what, 6? And then afterwards, the skater plus the cat, right? So that's 1.2 plus the cat was what, 800? 800 grams, so that's going to be 0.8 kilograms, or 2 kilograms times its velocity. So the velocity afterwards of the combo is going to be 3 meters per second. All right, and then we're going to lose some energy here. You know, it says how much energy is lost. It's possible that we don't lose energy. But we know, since this is called an inelastic, completely inelastic collision, we know that because it sticks, right? The cat is going to stick onto here. So they're moving off kind of together. So it's completely inelastic. We know there will be energy lost. We'll go ahead and prove that right now. So 1/2 times 1.2 times 5 squared, that's the initial energy, right? So that's going to be 0.6 times 25. That gets me 15 joules. And then afterwards, we have 1/2 mv squared afterwards. So it's going to be 1/2. Their combined mass was 2 times 3 squared, right? So it's going to be 9 joules afterwards. So you can see that we clearly lost some energy. The amount we lost is 6 joules. Okay, and again, that's going to be called a completely inelastic collision. So in this problem we have two cars. Again, they're in a head-on collision. Again, they're going to stick together here. Now what's different in this problem is we know the final velocity. So the final velocity is going to be 5.22 meters per second west. And what we're looking for is what is the initial velocity of the second cart. So how fast is this cart moving? Okay, but we'll solve the problem the same way. It's just our unknowns are going to be different. So for example, this first one's going to be 1500 times 10 meters per second. That's the momentum of that one. The second cart's going to be, well, we don't know the velocity, so we'll write it as 2550 times v. And then the combined, again, we're going to combine these masses all together, right? So 1500, oops, I messed that up, didn't I? This is 1550. 1550, oops, let's make that correction. 1550 plus 2550, and then their V combo. Now again, we're going to make this negative because it's moving west. Okay, in the opposite direction of the car moving at 10 meters per second. Okay, so this one's going to be 1550 with a 0 plus 2550, and then this one, let's combine this all together, right? So that's going to be 1550, 0, 0, 5, 1, 2, 4. Hope I did that right, times negative 5.22. This one I better use a calculator for. So 4100 times negative 5.22 gets me negative 21,402. Negative 21,402 kilogram meters per second. And oops, I forgot that V right there. Okay, so let's go ahead and do the math on this. VC, I'm going to let you do the algebra. You want me to? Alright, fine, I'll just do it. So we are going to subtract negative 1550, right? Negative 15,500. And that's going to equal 2550 times VC. Okay, equals, let's go ahead and do that out. So 21,402, 15,500 gets me 36,902. And then we'll go ahead and divide by 2550. So divide by 2550, and that should get us 14.5. Let's go ahead and double check. 2550 negative 14. It's a negative 14.5 meters per second. Okay, and then lastly we're going to find the energy lost. Okay, again, the type of collision. Again, whenever they stick, we know that's going to be completely inelastic. Whenever that happens, we're going to have energy that's lost in the collision. So we'll just go ahead and prove that here by checking the kinetic energies before and after. Alright, so we have 1/2. I'm going to run out of space, I already know it. So we're going to have 1/2 1550 times the velocity of 10 squared plus 1/2 2550 times 14.5. Remember, there's no such thing as a negative kinetic energy. And you'll see even if you just square that negative, you'll end up with a positive number anyways. So that's going to be our starting energy. That's going to equal E final, KE final, plus E lost. So let's go ahead and do that out. So I'm getting a starting energy total of 345,569 joules. We'll go ahead and keep it unrounded and then round it at the very end. Plus, so that's going to equal 1/2 times 4,100 times the final velocity was 522 squared. Okay, so we'll do that math out, and I get about 55,859. So you can see we end up with way less energy than we started with. So we'll just go ahead and subtract those two, and we're going to get, let's just round it at this point. So 345 minus 558, I get about 289,709, or approximately 290,000 joules. Alright, next problem. Alright, so this question, we have a 5 kilogram car. It's going to collide with a 15 kilogram car. This time, though, they do not stick together. After the collision, the 5 kg car is going to move off to the left with a velocity of 11 meters per second. So hopefully you know conceptually that that means that the 15 kilogram car is going to move off to the right. And the question is, how fast is it moving? So as usual, we'll just use our P initial equals P final. So the first one, we have 5 kilograms times 25 meters per second plus 0, since that cart has no momentum. Then afterwards, this cart has 5 kilograms, and it now has a negative momentum. So even though the problem doesn't say so, it does actually say so, because it says it's moving to the left. So that tells you that it's going to have a negative momentum here. Then we're going to add 15 times this cart moving to the right. Alright, so the initial momentum of the combination is 125. The momentum of this cart is going to be negative 55 kilogram meters per second plus 15 times v. Alright, so notice that this has to have a lot more positive momentum than this, because when you add them up, they have to add up to 125. So in fact, this is going to be, what, 180? Should equal, that's how much momentum this basically has, 180 kilogram meters per second. So for that to be true, the velocity must be 18 divided by 15, or 12 meters per second. Okay, now I didn't write the direction, but you know, we already talked about it. It clearly has to be right. You can tell just mathematically, since we ended with a positive number, that tells us that it's going to be to the right. So notice this time it doesn't stick, so we want to figure out what type of collision it is. To do that, we're going to do kinetic. We're going to do our kinetic again, compare our kinetics. This time, though, we actually don't know if it's completely elastic or partially inelastic. So we're going to kind of compare the kinetic energies. So the first one, we have 1/2 times 5 times 25. So the first one, 25 squared, so what is that? 0.5 times 5 times 25 squared. So the first one has a starting energy of 1,562.5 joules. Now after the collision, the first cart is going to be 5 times 11 squared. Okay, so 5 times 11 squared means it has 605 joules. Plus the second cart, which is 15. Oops, I forgot that 1/2, didn't I? So let's 1/2 that. So that's going to be, what, 302.5. Okay, the second one is going to be 1/2 times 15 times its velocity that we just calculated, right? 12 squared. So 0.5 times 15 times 1 squared is 1080. So notice the second one has 1382.5 joules. Okay, so the answer is we did lose energy, right? We started with 1500, we ended with 1300. In fact, the amount of energy we lost is 180 joules. So that means this is not completely elastic. This we would call partially inelastic, because number one, they bounce. Number two, we lost energy. If we had lost no energy, if that was the case, then we'd know that it's completely elastic in that situation. All right, moving on. All right, so in this problem we have, again, a collision problem where a 2 kilogram ball is going to collide with a 4 kilogram ball at rest. This time, though, the 2 kilogram ball is going to move off at an angle. So it's going to move with a velocity of 2.2 meters per second, but it's going to move off at an angle here of 34 degrees. And so what we want to do is find out, well, what's going to happen to the 4 kilogram ball. So one of the first things you should do is just predict what it's going to do. So we're going to predict that, well, it's going to move like this. That would be the most logical thing. Now, if you're wrong, the math will tell you you're wrong, but you have to start somewhere, okay? All right, so this is a two-dimensional problem. So into two-dimensional problems, we're going to have, we're going to do P initial equals P final, but we're going to do it with both the X and the Y direction. So P initial in the X direction should be equal to P final in the X direction, and the same thing in the Y direction. So let's do the X direction first. So notice that the red ball is moving completely horizontal. So all its momentum is going to be horizontal. So 2 times 4. So that means the starting momentum of this is 8. This ball is starting from rest, so it has no starting momentum. So the starting momentum of both is going to be 8. Okay, and then after the collision, notice that this one is at an angle. The red one's at an angle, so it has some velocity this way. I'm just going to simply call it Vx. Maybe we'll call it V2x just to signify that's ball, 2 kilogram ball. So the P final is going to be the 2 kilograms times, we'll call it V2 in the X direction, plus, same thing with this green ball here. The green ball also has a V, we'll call it V4 in the X direction. So that's going to also have a velocity, momentum of 4 times V2, V4 in the X direction, right? Now V2 in the X direction, we can go ahead and solve that. So let me go ahead and do this off on the side. So notice this one is moving at 2.2 meters per second, and the angle is 34 degrees. That means this horizontal velocity, we could write that as 2.2 cosine of 34. And while we're at it, let's do this one. This one would be 2.2 sine of 34. So let's go ahead and do these out. So this horizontal velocity is going to be 1.82 meters per second. And this vertical velocity is going to be 1.23 meters per second. Alright, so that means the momentum of this ball is 2 times 1.82 meters per second. Okay, and then we'll just leave this one alone, 4 times V4x. So notice what we can do. We can go ahead and solve for V4x. I'm going to leave it to you to do this, to do the algebra on this one. So I'm going to go ahead and do it, and I get a velocity of 1.09 meters per second. So again, that's the V4, the velocity V4 in the X direction. So we're going to repeat this in the Y direction though. So we do the same things. Now notice, since there's nothing moving in the Y direction, that means there's no initial y velocity, no initial y momentum. Okay, but there is momentum afterwards. Okay, so we have the momentum of ball 2 plus momentum of ball 4. Now how's that possible? Well, ball 4 must have a negative momentum. Okay, so ball 4, in other words, must be moving downwards, which is what we can see. So we'll go 0 equals, so P2, that would be the mass of ball 2. Now we already found the y velocity, that's right here. So that's 1.23 meters per second. That's the velocity in the y direction. Plus 4, that's the mass of ball 4, times its velocity. And we'll just call this V4 in the y direction. Okay, so notice we're going to get a negative number here. If you want, you could plug in the negative to start with. I like to let the math tell me it's going to be negative here. So let's go ahead and do that. So V4y, do the algebra, 2 times 1.23 divided by 4 gets me 0.615, or negative 0.615. Alright, now ultimately we want to find the total velocity of ball 4. So let me shrink this down just one more time. So again, we said ball 4 was going to go like this, and it looks like we're going to be right in that prediction. So in other words, we saw this was 1.09, and we saw this was going to be down here, right? So I'll write it as negative just so you can see that it's moving down. So our prediction was right. If, for example, our x velocity was negative, then that would tell you that maybe it goes back. So maybe this is ball 4, this is ball 2, this could possibly go like that. Now it's unlikely that that would happen, but it is possible. It doesn't violate the laws of physics, because momentum still can be conserved. Now let me just point out one thing while we're here. What will violate the laws of physics is that this ball goes like this, and the green ball also goes like that. That is impossible, because we had a y momentum of 0. That means there has to be some positive momentum in the y direction and some negative momentum to cancel out. Contrast that with this other weird one. This one's possible. Notice that we could cancel the y momentums, like this one can cancel with this one. And we can have a net x momentum, because if this was like huge this way and then just a small amount of momentum backwards, that could still sum up to have a positive momentum in the x direction. All right, let's get back on track. So we're just going to solve for this v total here. So we'll just use the Pythagorean theorem. So 1.09 squared plus 0.615 squared, we'll square root that. That gives us our C, or V total. So I get 1.25 meters per second. Now we also want to get the angle here. So for that we use our tangent function. Tangent of theta, or theta equals to inverse tangent, equals opposite, which is 6.15 divided by 1.09. Okay, so I just realized this should be 0.6, okay, 0.6, and I'm actually getting 29.4 degrees, and we'd call this south of east. So I notice it's slightly different from the answer key. Sometimes there's rounding errors, but you know, as long as we're close, we know we did it right. All right, let's move on to the next one. All right, here we go. This is probably the hardest problem of our problem set today. So if you weren't able to solve it on your own, don't worry, it's a tough one. So in this case, we have two balls colliding, and one ball is going to move off at an angle. Let's call this ball A. This one's going to move off at an angle of 30 degrees this way. And then ball B is going to move off at an angle of 60 degrees this way. And this time we're looking for those velocities, so we're trying to find out how fast they're moving afterwards. Alright, so we're going to do conservation of momentum once again, and then since we do have 2 dimensions, we're going to do 2 dimensions again. So for example, we're going to have P initial in the x equals P final in the x. So P initial in the x, so again, only one ball is moving horizontally, so that's the 2 times 5, so there's going to be 10 kilogram meters per second of momentum in the y direction. And then in the x direction. And then in the y direction, same thing, except there is no initial momentum, right? Because there's nothing moving vertically before. Now after the collision, you have 2 things moving in both the x and the y direction, right? So the way I'm going to solve this one is as following. Mass B, I'm simply going to call that VB, and then mass A, I'm simply going to call that VA. And then what I'm going to do, actually let me just try this. Let's zoom in first. Zoom, 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 zoom. So what we're going to say is this has a V horizontal velocity, right? And what I'm going to call this is VA cosine of 30 degrees. And I'm going to do this for all 4 of these dimensions here, or directions. So for example, in the y direction, we could write this as VA sine of 30 degrees. And then for the red ball, or for ball B, we're going to go, this has a horizontal velocity. We're going to call this VB cosine of 60. And then this is going to be VB sine of 60. Technically speaking, this is down, right? So this would be like a negative velocity. So we're going to just make sure at some point we take that into account. Alright, let's zoom back out here. And then let's just kind of put these into place. So for example, over here, we're going to say this VA was, let me just color code it so you can see it a little bit better. So this is going to be 2, oops. What just happened? This is going to be 2 times VA cos 30 plus the green one. The green one was 4. Sorry, no, it's also 2, isn't it? I made that kind of easy. So that's going to be 2 VB cos 60. Okay, now notice we have 2 unknowns here, but in our y equation, let's go ahead and do the y equation, you'll see what I'm talking about. On the y side, we have VA sine of 30 plus, then this one, remember we said it was coming down, so we're going to take that into account. So we'll say that's negative VB sine of 60. So we have 2 equations, 2 unknowns, right? So we should be able to solve for one and substitute it in for the other. Okay, so let's go ahead and do that. This one looks like it's going to be easier to solve and substitute. So in other words, we could write this as VB sine 60 equals VA sine 30, or VB equals VA sine of 30 over sine of 60. Now remember, this is just a number, so to be honest, I'd just recommend just doing the math on that. So I'll go ahead and do that now. So I get VA times 0.577. You could leave it in terms of sine 30 and sine 60, but sometimes it's easier just to, remember that's just a number, right? So we can just do the math out on that, and then it'll kind of keep things a little bit cleaner as we go. Alright, so let's go ahead and then substitute in there for VB. So we're going to go up here, we're going to substitute that in for VB. So this would be 2, actually, you know what, let's simplify this further. Look at that, 2, 2, 2. Okay, so it's just going to be 5 here. Just save ourselves a little bit of math potential difficulties. So VA times cos 30 plus, and then we're going to just substitute in that VB. So remember that was 0.577 times VA times cosine of, what's that, 60? Okay, so again, we could just kind of do some math here if we wanted to. So for example, cosine of 30 is, that's just, what, 0.866 or something? Cos 30 is, yeah, 0.866. And then we'll just do the math on all of that. So plus VA, so 0.577 times cosine of 60. Oh, cosine of 60 is just 0.5, right? So it's half of that. So 0.2885. So that equals 5, right? So in other words, 5 equals, if we add those two together, 0.8866 plus 285 is basically about 1, right? 1.15. So that means VA is going to be 4.33. Okay, and yep, let's check the answer. That's the correct answer. So VA is going to be 4.33 meters per second. And then at this point, this should be really easy. We're just going to go ahead and throw that right into there to solve for VB, because we already derived that equation for VB, right? So VB equals 4.33 times 0.577. Okay, and that gets us 0.577 times 4.33 gets me about 2.5. I'm getting 2.499. Yeah, so we'll go 2.50 meters per second equals VB. All right. So yeah, that's a rough one, but that's how I recommend you do it. You just kind of break down your triangles into the components, substitute it into your X and Y direction, and there you go. All right. Let me know if you have any questions about that one in the comments below, and I'd be happy to highlight that for you. So this problem is what we refer to as a ballistic pendulum. So essentially what we do is we fire a bullet into a block of wood, and we typically have that block of wood attached to like a string or something where the wood can pivot, where there's like a pivot point right here. And what's going to happen is when the bullet hits it, this little block of wood's going to kind of rise up here. And knowing that, we can figure out how fast the bullet was moving. Okay, actually knowing the angle that it moves at. So in this problem, it tells us that there's a 40-gram bullet and it's firing into a 6-kilogram block of wood. The angle that it reaches is going to be 22 degrees. And yeah, and then the string length is 2 meters long. So we're going to try to figure out several things. Ultimately, what we're looking for, honestly, is letter C. What's the velocity of the bullet before? That's the purpose of this ballistic pendulum, to figure out how fast the bullet's being fired out of the gun. All right, but we're going to break it down into kind of baby steps here. So the first part is to figure out what's the maximum height that the bullet reaches. So in other words, we're looking for this height up here, how high it goes. So we're going to just use a little geometry actually to figure this problem out. So let me kind of do this off on the side. Actually, let's just kind of shrink it down so we have some more space. Okay, so if you imagine, like, here is the 2 meter long string, right? And then this goes up here. Now the string doesn't change, so that means this distance is also 2 meters. This was 22 degrees. Okay, so notice if we just draw a triangle across like this, then we can figure out this little side in here. We can figure out this side, right? Just using some trigonometry. So this side here, this would be 2 cosine of 22. So 2 cosine of 22 gets me about 1.85. So what that means is that this height here is going to be, 2 minus 1.85, or about 0.15 meters. So that's going to be the height of the block, or where the block ends up, 0.15 meters. Okay, so that's going to be letter A. We just solved A here. So letter B then, we're going to find out, well, how fast was this moving right after getting hit by the bullet? So for this, we're just going to use conservation of energy. So notice that this block has some kinetic energy after being hit by the bullet. And then as it rises up, that's changing into gravitational potential energy. So for B, we're just going to use energy conservation. So we have kinetic energy after getting hit by the bullet. That's going to change into gravitational potential. So 1/2 mv squared equals mgh. Notice our masses cancel. So let's try to find the velocity. That's going to be 9.8 on Earth, and the height we just calculated to be 1.5. Okay, so do the math here. I'm getting, let's see, 2 times 9.8 times 0.5, 0.15, and then square root that. So I'm getting about 1.7 meters per second. So that's how fast the bullet, so it's after the bullet's already hit, right? So it's after the bullet has hit. The combination is then going to be moving 1.7. Oops, that's not kinetic, is it? 1.7 meters per second. And then that's going to cause it to rise up to that 0.15 meters. Okay. All right, that moves us to C, and this is actually the momentum part of the problem. So here we're kind of going backwards if you noticed. So our P initial equals P final. Now what we found was the momentum afterwards, right? So that would be 6, and then we'll go ahead and add the mass of the bullet, even though honestly it's probably negligible. 6.04 times its velocity, which we got to be about 1.7. So that's the momentum of the bullet and the block combination after the bullet has collided. Now before, it has a momentum of 0.04 times whatever velocity it's moving. And that's it. So the momentum before equals the momentum after, and that's going to help us get the velocity. So 6.04 times 1.7, and then we'll go ahead and divide by 0.04. And that gets me about 256, 257. Here it says 255. I know we've been rounding differently throughout, so I'm going to put what I'm getting, which is 257 meters per second. That's how fast the bullet was moving before it collided. All right, last one. This isn't really a part of the unit, but I'm going to throw it in anyways, and that's what's the period of the pendulum. So for this one, it's just a simple equation. So the equation for the pendulum is T equals 2 pi. The period of a pendulum is 2 pi square root of the length of the pendulum times little g. So 2 pi times the square root of our length, which was 2, divided by 9.8. All right, and you get 2.84 seconds. So again, the reason we do this is we're actually trying to find the velocity. How fast is that bullet moving? And in this case, we do this experiment, we got 257 meters per second. All right, let me know if you have any questions. All right, in this problem, we have a soccer ball moving 18 meters per second to the left, and then a player is going to kick the ball and cause the ball to now move. Remember, we have pretty much always a before and after in all these cases. So the before is the ball moving to the left, The after is the ball moving to the right, and the ball is moving to the right with a velocity of 22 meters per second. Okay, so the first thing is we're going to figure out the impulse on the ball. Remember, impulse can be written two ways. It can be written as the force times the change in the time, and it can also be written as a change in momentum. Now in this case, they don't tell you the force, right? So we're really going to find the change in momentum to figure this out. So the change in momentum is going to be basically the final momentum minus the initial momentum. So the final momentum is going to be 0.4 times 22. Now the initial momentum, actually you got to be careful. Initial momentum, notice here that we're moving to the left. So that means we're starting out with a negative momentum. So the initial momentum is actually going to be 0.4 times negative 18. Okay, so in other words, 0.4 times 22 gets me 8.8. And then negative 18 times 0.4, that gets me negative 7.2. So notice we're subtracting a negative. Really what we're doing is we're adding. So 7.2 plus 8.8 means the actual change in momentum is a full 16 kilogram meters per second. So notice, since we're changing, here's the key concept here, guys. So we're moving to the left and then we're moving to the right. That's a big change, right? If we just went to the left and stopped, that would be a change of whatever this was, 8.8, right? But if we're moving to the left and then to the right, that's a huge change, or bigger change. So that change is going to be 16. So that's our change in momentum, but it's also our impulse, because those two are the same, right? So our impulse and our change in momentum is going to be 16. Now to finish up this problem, they're just asking, well, how much force must be exerted? Well, since we know the impulse is 16, and we know the time to be 0.04, then it's very easy to find the force, right? We'll just plug it in and solve for the force. So I get a force of 400 newtons exerted by the foot on the ball. Okay, here's a bonus question. How hard does the ball hit the foot? Put your answer in the comments below. All right, the final question. We have a guy that is dropping from rest into water, right? So here, let's just draw this out. So here's our guy, and he's going to drop, he's 82 kilograms, and he is 3 meters above the water. So this is 3 meters, and then we have our water here, right? So our water is going to be below, and then he's going to come to rest. So he hits the water, right? And then he comes to rest. Let's just put him here. Here's the guy coming to rest, and it takes him 0.55 seconds to come to rest. So the question ultimately asking is, what is the force on the man? Okay, so this is kind of a two-part problem. The first thing we want to do is we want to figure out how fast is the guy moving here. Actually, just think about it in reverse. If we're looking for the force, remember our impulse is force times time. If we're looking for the force on the man, that's going to be equal to the change in momentum. Well, to find the change in momentum, we need to know the mass of velocity before and after the man hits the water. We know the velocity afterwards, right? The velocity afterwards is going to be 0 because he stops. So we want to find the velocity before he hits the water, and therefore we know the momentum before he hits the water, and therefore we can find the impulse. Okay, so to do that, we can just use, either kinematics or energy, however you want to solve it. Me personally, I like using energy. So initial equals final. So in other words, at the top he has all potential, at the bottom he has all kinetic. So mgh equals 1/2 mv squared. Masses cancel, so we got 9.8 times 2 equals 1/2 times his velocity right before hitting the water. So I get 6.26 meters per second. That's a velocity right before hitting the water. Now, technically speaking, this is down, right? So if we want to keep our signs correct, I would write this as negative. But the key idea is moving down. So back to what we said before, if we want to find out how much force is exerted on him, we're just going to look for that change in momentum, right? So J equals Ft equals change in momentum. So as stated before, changes final minus initial. Whoops. And the final we said is 0. So the initial would be minus the mass, which is 82, times his final velocity, which is negative 6.26. So 82 times 6.26 gets me negative equals 513 kilogram meters per second. Okay, and then that equals force, and the time was 0.55 seconds. Okay, so we'll divide by 0.55, and so if we get the same answer they got, 933. That is not what they got. What did we do wrong? Ah, I see. So I made a minor mistake somewhere. Instead of me fixing this video, you know what I'm going to do? I'm just going to leave it, and you try to find the mistake. If you can find the mistake, put it in the little comment section below, and I'll confirm it with you. But yeah, it's a pretty easy mistake, simple, dumb mistake that I made. Pretty common. So go ahead and take a look, and yeah. Alright, hope that was helpful. Please let me know if you have any questions, and I will talk to you later. Bye-bye.